All right, so today I'll be presenting on capillary and electromagnetic Smallsat propellant positioning. All right, so first, just a quick overview. I'm going to start off with the motivation for why we're looking into these devices, and then we're going to look at the natural fluid behavior, and then we're going to look at how we can make the fluid behave in ways it doesn't want to. Then we'll move on to a comparison of all these different methods, and we'll end on some conclusions. Okay, so first, the motivation. Propellant positioning is required anytime you use a liquid propellant in space. You need to know where that propellant is if you're going to consistently extract it from your tank. Now, we're pretty good at this for traditional axisymmetric tanks with liquid propellants and a separate pressurant gas. However, we find that there are challenges when we try to do this on smallsat cold gas propulsion systems. The first challenge being that we use conformal tank geometries. So if you take a look at the bottom left image here, that is the visor's propulsion system. And as you can see, its tanks are not axisymmetric. It is a conformal geometry. Next, we use two-phase propellants often in these systems. And that presents a whole host of problems that we will discuss later in this presentation. Now, as I've already shown, there are systems that are using conformal tank geometries with these two-phase propellants, and they're working somehow. And so they do have a propellant management device that they're using, but it can be fairly volumetrically inefficient and they can require high power. And for an example, I've presented the Marco-MIT propulsion system designed by VACO. It's on the bottom right here in diagram. And so we see on the left, they have a large tank. This tank stores the majority of the propellant as a two-phase mixture, so it's a liquid vapor mixture. And then there's a smaller tank on the right where they store just a vapor. So when they want to fire their thrusters, they draw vapor out of this vapor tank. And when the pressure in that vapor tank runs low, they're able to replenish it from their main large tank. And to do this, they route liquid propellant through a heat exchanger where it vaporizes the propellant. And that vaporized propellant goes into the vapor tank, and you're able to continue firing. Now, like I said, running that heat exchanger could be fairly power intensive. A back of the envelope calculation shows that for a 20 millinewton thrust level, one could expect a minimum of 7 watts of power to vaporize that liquid. So this is not great. We don't especially like high power on small satellites. It's also volumetrically inefficient because of this plenum, this vapor tank. Storing a vapor is just volumetrically inefficient. It's not very dense, and so you need a large volume to hold a small amount of it. For those reasons, we're looking into improved systems. All right, so now we're going to get into our problem, kind of the specific use case that we're going to be looking at for the rest of this presentation. So we're going to use a 3U propellant tank, shown on the left here. And we're going to assume this propellant tank is used on a CubeSat propulsion system. And we're going to assign this system the performance characteristics of the BioSentinel propulsion system. It recently flew on Artemis 1, so it's nice and topical, and also was designed by our lab, so I know all the performance details, which helps a lot with the analysis. Now, this system uses R236Fa as a propellant. This is a refrigerant that we store as a two-phase mixture, so it's a liquid vapor mixture. And the whole point of this talk is we're trying to extract vapor from this tank. That's our one goal, is we want vapor consistently extracted from the tank to route to our thrusters. Now, in order to do that, there's sort of there's two criteria we need to meet. And this is how we're going to evaluate all of the propellant management devices we look at for the rest of this talk. First, you need to initially position this bubble over the outlet of the tank. Then you need to maintain its position there during operations. So I have a little bit of information about the system and the propellant listed here, but the big takeaways are, first, the thrust level is fairly small. We're looking at 15 to 90 millinewtons, and that thrust level varies with the temperature of the system. Next, the propellant properties. Again, I just want you to take away that they vary a lot across our operating temperature range. And this is partially because we're stored as a saturated mixture, so we're always at our saturation pressure, which again varies fairly dramatically with our temperature range. All right, so with that said, what if we don't do anything? What if we just put propellant into the tank and we hope there's somewhere where we can put the tank outlet where it'll always extract a vapor, and then our job's done for us, and that would be just dreamy. So to see if this is the case, we model the system in SE-FIT. SE-FIT is a free software, and what it does is it finds the minimum energy surface for a fluid system. And it takes into account capillary forces, gravity, accelerations, all sorts of different forces. If you can program it into SE-FIT, it will minimize it for you. So on this upper row, we see a series of images. The colorful bubble, that's our vapor bubble. So that's what we need to be extracting from the tank. So on the upper right, we see a 70% fill fraction. Now, a 70% fill fraction just means it's 70% liquid in the tank and 30% vapor by volume. And this is our non-accelerated case. So no thrusters firing, just orbiting the Earth. So in this case, we see that for the 70% fill fraction, we form a nearly spherical bubble that sits right in the center of the tank. And we expect a sphere because a sphere has the minimum surface area and therefore the minimum energy for this case. But now we see as our vapor bubble grows, it's going to form this more oblong shape. And throughout all four of those images, we see that the bubble is always touching that sort of elbow of the propellant tank. So one might initially think, all right, let's put the propellant outlet there and we can consistently extract a vapor. However, you immediately see that that would be a problem when you move down to the second row. So this is our accelerating case, and this is the acceleration we see with our minimum thrust. So the lowest acceleration we will experience while firing. On the bottom right, you can see that our bubble is now pushed to the top of the tank by that acceleration, and it is no longer touching the elbow of the tank. So right away, you see we could not extract a vapor from the tank by just having the propellant outlet in the elbow. And in fact, the bubble won't reach that elbow again until we're down to a fill fraction of 50%. So half our propellant is gone before we ever touch that elbow again. So this is a problem because it means there's not a single place that we could put the outlet of the tank where we could consistently extract a vapor. So we need to do something about this. Now, propellant management devices are our solution to this problem. All right, so the first device we're going to look at is a capillary system. Now, capillary systems work by using surface tension to control the position of a liquid propellant. They're very commonly used in traditional tanks, specifically your axisymmetric tanks with a liquid propellant and a separate pressurant gas. They've got a lot of heritage. We've been using them essentially since we've been managing fluids in space. So they're very well documented. Now, there are inherent issues with using them in our system, though. I'm going to outline them here. First, we're trying to position a vapor bubble, not a liquid. This has been done before, but it is more challenging. The next challenge would be that we're using a conformal tank geometry. And this sort of couples with the problem of positioning a vapor. We might get into that a little bit later. And then the third problem is that there are going to be many small vapor bubbles. And while capillary systems are great at positioning one large bubble, they struggle with positioning these smaller bubbles. Now, the reason for all these smaller bubbles is twofold. First, when we extract vapor from the tank, the liquid that's left in the tank is going to begin to boil. And the reason it does this is because we're stored at saturation pressure. So it's going to boil until it reaches that equilibrium saturation pressure again. All right, so when it does this, that boiling is going to be concentrated along the walls. And so you're going to get lots of small bubbles forming all over your walls. So just from that alone, you'll have many small vapor bubbles. Now this can also happen due to a thermal gradient in the tank. So if we heat up one side of the tank, and the other side remains cool, we'll see vaporization on the hot side and condensation on the cool side. And this again serves to create a lot of small bubbles within our tank. Now, the exact reason that it's hard to position these is demonstrated well in this YouTube video that we're going to take a look at here. So here we have our astronaut, and he's making a cup of coffee in space. And so he's injecting the coffee into the specially designed mug that uses surface tension to trap the liquid in that left-hand half. And it does that using this sort of wedge geometry. Now, you see there's lots of small bubbles in that area. Now, if the bubble is small enough that it's not touching any of the walls of the coffee cup, it actually won't be forced out of that liquid by the wedge geometry. The capillary forces only work if the bubble is touching a wall. And so you can see here, even now the liquid has essentially stopped moving, any small bubbles still remain behind. Now, the same thing is the reason that our capillary device will not work. If we did want it to work, we need to make sure that there were fins in our propellant management device so close together that no bubble could exist without touching a fin. And so very quickly, this turns into you having more propellant management device than you do fluid, which is obviously not desirable. Now, it should be noted that this propellant management system would be capable of keeping one large bubble positioned at the top of the tank. It just won't be able to drive these small bubbles up there to do that. So if we could get it into one large bubble at the top of the tank, this would work great. But the capillary system alone won't be able to do that. So we look at how we can improve it. The first thing that we're going to look to as an improvement is the addition of a heater. Now, what's going to happen here is what I described before with a thermal gradient across the tank. We're going to put a heater right by the outlet of our tank, which we're going to take to be at the top of the tank for the rest of this talk. Now, by putting the heater there, we're able to cause vaporization at the top of the tank and condensation all throughout the cooler propellant management device. So with this, we've created one large bubble at the top of the tank, and we can design a capillary system that can maintain that bubble there. And I have an example of one such system shown here. Now, this system is just a rough initial pass at a capillary PMD, but by putting it into SE-fit, we were able to show that it will position a vapor bubble as shown here, sitting at the top of that tank. And so as long as we can get the bubble there in the first place, this system can hold it there. So that's great. We've got a system now that would work, and we can consistently extract a vapor from the tank. And we're happy about this. However, the system is not perfect. It's likely that it won't be very robust against small liquid droplets or foam. Now, these droplets are going to happen because when you boil a propellant that's in a two-phase fluid, we have seen from the NASA tank pressure control experiment that it can be rather dramatic and chaotic. So you'll get small droplets sort of flying across as you get these rapid boiling events. If one of those small droplets were to pass in front of our propellant outlet, right when we were to begin to fire the thrusters, we could suck that droplet out of our tank, and now we've extracted a liquid, and that's the whole thing we're trying to avoid here. So that is not great. Also, there is the potential for foaming. So as the propellant begins to vaporize while we're firing, we might see a foam generate, and for the same reasons as the droplet, we might extract a little bit of that foam. So that's not ideal. However, this system very likely could work and probably most of the time would work. As for the performance of the system, the capillary PMD takes up 232 grams, 86 cc's. It's going to use at least 5 watts for 108 seconds, and that's to create that, that initial bubble. And the analysis for this is shown in the paper. All right, so with that said, I just want you to keep those numbers roughly in mind, about 200 grams, about 90 cc's, and a fair bit of power. So now that we know that the capillary system is not entirely robust, we look into electromagnetic PMDs. We try to answer the question, are body forces better? The first system we're going to look at is a magnetic positive positioning system, or MPP system. Now these work by exerting a body force on the propellant. Essentially, any fluid that's in a magnetic field gradient will feel an inherent body force. The equation for that is shown there, neglecting a couple of terms. And this has already been demonstrated in microgravity. So we've seen that the position of a bubble can be affected by a gradient in magnetic fields. Now, an exciting thing about this is you can actually use a permanent magnet. In the source I have cited here, they use a roughly 1-inch diameter and 3/4 inch tall neodymium magnet, and it quickly affects the position of a bubble in microgravity. Now, diamagnetic liquids are repelled by the magnet. So by repelling the liquid from the magnet, a sort of magnetic buoyancy force is created, which causes the vapor to be attracted to the magnet. All right, now this sounds great. We could use this system to capture a bubble of vapor around a magnet. So if we put that magnet right over the outlet of our tank, concentric around that outlet, we can ensure that there's always a vapor bubble over our outlet. And that would be great. However, we see in this figure on the bottom left, this is a COMSOL simulation of that system. We see that the acceleration of the liquid away from that magnet drops off very quickly as you move away from the magnet. So even just this 0.5 view rectangle, just 5 centimeters tall, 10 centimeters wide, we see that there's very little acceleration felt, even just 5 centimeters from the magnet. So now one can imagine that if our vapor bubble were in the bottom right half of our tank over here, it would feel almost no force, and we would almost certainly not be able to do that initial repositioning that I've discussed. So if we were to get the vapor bubble over the magnet in the first place, we could hold it there, but this system alone is not going to be able to drive that bubble up towards the magnet and over the inlet. So we'd like to do something about this. And we can again revisit our old friend of the heater. And we're going to use it exactly the same way we did in that capillary system with the heater. So we'll turn on the heater, and it'll vaporize the propellant near the outlet of the tank, and propellant will condense in the cooler parts of the tank. And by doing that, we've moved our vapor bubble over the outlet and right by our magnet. Now the magnet is very capable of holding that vapor bubble there. And by doing this, we've created a robust system. It's robust in the sense that the magnet is applying a body force. So those small droplets and foams we were worried about before are not so much of a problem now, because a small droplet doesn't have to touch anything like it did with the capillary device. Just simply by being in the magnetic field, it is going to feel an inherent body force on it. Also, this body force is going to get stronger as you move closer to the magnet. So if you imagine a small droplet that is for some reason moving towards the magnet, the force on it is increasing and increasing and increasing as you get closer. And this should be sufficient to repel any liquid that's trying to leave the system. Additionally, these magnets have been shown to be able to cause a foam to condense and sort of break down, which is good because, again, we were worried about foaming in that capillary case. So this solves a lot of our problems, and it's also less massive and a smaller volume than the capillary system. So this is only 72 grams as opposed to about 200, and it's only about 10 cc's as opposed to about 80 or 90. So that's great for us. The only downside here is we're still using a fair bit of power to run that heater. So now we look to another option, a dielectrophoretic or DEP system. And thus, this works a lot like the MPP system in the sense that it uses a gradient in fields to apply a body force to the propellant. However, in this case, we're using a gradient in the electric field. Now, it has been shown that for dielectric fluids, the liquid is attracted to the areas of high electric field intensity and the gas is repelled. So in order to operate this as a sort of PMD, what we need to do is generate really high electric field intensities in the lower part of the tank and much lower intensities up near our outlet. And we can do this as shown on the bottom left. So essentially we have alternating rows of high potential 1 kilovolt wires and ground wires. And so this is a nice cross section of that system. So to model how this system would work, we again do a COMSOL model that you can see on the bottom right. And we see that the liquid is very strongly attracted to these wires with very high accelerations near the wires that drop off as you move away. That's much like the magnet, but the nice thing here is that wires are very light, so we're free to add as many wires as we want. And I'm going to comment here that this system is not entirely new and novel. It was proposed in the 1960s, but they quickly abandoned it due to scalability and safety concerns. So in a large tank, you need very high potentials. And as one might imagine, when you have these very high potentials that can cause arcing within your tank, people get a little nervous. However, our tanks are small, so we don't need nearly as high of a potential, and the risk of arcing is significantly reduced. Now, a little more on these systems. One of the interesting things about them is they're very adaptable, and they're adaptable through positioning of the wires and by changing the potential of those wires. Now, this can be done either dynamically or statically, but it opens up a lot of interesting potentials that are discussed further in the paper. And analysis indicates that this system is going to be able to initially reposition that bubble and maintain its position, which were our two main goals. So that's very exciting. However, this system is the least mature of the ones that we have discussed. And there's a lot of further development that needs to be done even to estimate the size, weight, and power of this system. So for example, this system will need a power processing unit to generate those high potentials we discussed. And this power processing unit has not yet been fully developed. So for the time being, merely just so we have some way of evaluating its performance, we analyze the mass and volume of the wires. Now these are 28 gauge wires. And so as one would expect, the mass and volume are very low. We're looking at 2 orders of magnitude less massive than the capillary system, and again, at least an order of magnitude smaller in the with regards to volume. Now, also it should be noted that this system is going to use a very small amount of power, and the reason for this is despite our high potentials, we have very little current flowing because we're not actually running a lot of current, we're just maintaining a potential. So again, we expect very low power, but without fully developing the power processing unit, that cannot be entirely analyzed. Okay, so now for a comparative analysis. We've talked about a lot of systems, but which one works best? And so we've analyzed them here. And this is a bit of an eye chart. So I'm going to start off by saying, first of all, green is good, red is bad. I'm now going to direct you to those last 2 columns. That's positioning and operation. Those are the 2 sort of performance characteristics we're really looking at. How well do we initially position that bubble, and how well do we keep it there while operating? We see immediately that the bottom 2 rows perform very well in these categories. Those bottom 2 rows are MPP devices with heaters and DEP devices. So now that we know they work well, we need to analyze how they perform in the sense of actually integrating them into a spacecraft. So the things we care about first would be volume, mass, and power. And we see that in our initial estimate, we expect the dielectrophoretic system to be very low volume, very low mass, low power, and these are all highly desirable characteristics. Now, then we look at maturity of the system, and we see here that the MPP system with the heater is more mature. We've demonstrated heaters affecting propellant positions in space, and we've demonstrated magnets affecting fluid positions. So the physics have been shown in the relative environment. They just haven't been coupled yet. However, a DEP system is much lower maturity. Now, they're roughly equally scalable for a small sat size system. So we now look at manufacturability. How easy is it to build these systems? Now, an MPP system with a heater is relatively easy to build. You attach a permanent magnet, concentric around your propellant outlet, you put a patch heater on it, and there you go. You've got your system. Not terribly hard to build. A DEP system, on the other hand, is going to involve stringing many wires across your tank and keeping them there, charging them up to high potentials, building a power processing unit. And while none of these challenges are insurmountable, they are all more difficult. So that makes it a more challenging system to manufacture. And so without declaring a full winner in that comparative analysis, we can see here that the DEP and MPP systems, as well as the thermal systems, are very enticing. Now, just to make some further conclusions, current propellant management devices are not well suited to two-phase propellants and conformal tank geometries. These new systems, though, could offer improved robustness and greater volumetric and power efficiency. This poses a very interesting and novel path forward for small satellite propellant management, as well as propulsion as a whole. And now, with those conclusions made, I'd like to make some acknowledgements. Firstly, I'd like to thank the National Science Foundation for funding me. Really appreciate the free school. I'd also like to thank Professor Stephen Collicott for his guidance in the use of Surface Evolver and SE-Fit. He's the expert of these softwares, and he was very gracious in helping us out. And with that, I will take questions. One thing I would like to note is that this GIF you see on the far right there is an SE-Fit simulation actually running in real time. And it, in roughly 30 seconds, is able to figure out the minimum energy configuration for this propellant bubble in an accelerating case. So very nice software, highly recommend it. If you have any questions or would like to see more about what our labs are doing, feel free to use any of the links presented here. And I'll thank you for your time.